Hi, everyone. I'm Bruce Poria with American Infrared Solutions. I'm the author of the Nyx Connect software, and today I'm going to walk you through the software's full feature set. Nyx Connect is designed to simplify OEM integration and give scientific and engineering users full control over raw system data. There are 4 levels of functionality and a variety of connectivity options. Let's quickly walk through them so you'll have a frame of reference during the tutorial. Level 1 is ideal for OEMs and engineers who simply want uncorrected 16-bit data and plan to provide their own image processing and sensor management. It supports AIR, smart IDCAs, and provides full control over the focal plane and the raw data. Level 2 adds gain and offset correction, persistent non-uniformity tables, and pixel replacement. At this level, you would use a third-party frame grabber or a Playora camera link to USB 3 vision converter to display the camera output. Level 3 offers tools that are useful for defense OEMs. These include lens control, bore sighting, diagnostics, and multiple video output options. Level 4 is well suited for OEMs, engineers, and researchers who want full control over the camera with an integrated image processing tool set. Level 4 does not require a third-party frame grabber. All that is required is a Windows laptop or desktop with a USB 3 SuperSpeed port. This tutorial will focus on level 1, 2, and 4, since those are the levels that are supported by Nyx Connect. Level 3 functionality will be covered in another video. So we're going to demonstrate the Nyx Connect software as it relates to the Nucleus camera, and the Nucleus camera can be purchased with either a USB 3 vision interface or a camera link interface. The camera link interface is used in conjunction with a third-party frame grabber, and the camera delivers 16-bit Canon offset corrected dead pixel replaced data to the frame grabber, and all of the range compression and snapshot capture and sequence captures are all managed by the third-party frame grabber. If we're using a USB 3 vision interface, then we have the option of eliminating the third-party frame grabber and using Nyx Connect exclusively. And there are 2 ways to get a USB 3 vision interface. The camera can be ordered that way, or the camera could be ordered with a camera link interface and a Playora iPort CLU03 camera link to USB 3 vision converter can be purchased from Playora Technologies so that the camera can interface to Nyx Connect directly. So let's open Nyx Connect. Now, when you notice when Nyx Connect opened that 2 windows open. One is the user interface for Nyx Connect. The other is a little command window. And the command window is basically the surface of a USB 3 vision image processing server that AIRS has created. And the user interface basically is the surface of the application that presents the user interface to the user. In this window on the right, we call that the command log window. You can see that we were searching for USB 3 vision devices, and then we found one. We started it streaming, and then we were ready to connect to the camera. We're not actually connected to the camera at this point. We're just ready to connect because we now have an interface to the camera. So let's do that. Let's connect. Now, You probably noticed before that all of the controls were grayed out. Now that we've connected to the camera, all the controls are enabled. We basically sent a series of inquiries to the camera asking about the camera's state, and then populated the user interface with that camera information. If at any point the camera fails to respond to a request for information or a command, it'll immediately disconnect from the camera and gray out all the controls. And we've done that so that you can be confident that if the controls are actually active and not grayed out, that all of the information that's displayed in the user interface is actually current and in sync with the camera's state. Otherwise, we might be showing stale information, and that's not ever a very good thing to do. You can reconnect to the camera at any time. There's not really any compelling reason to do that, but just so that it's understood, if you press connect again, we send all those same inquiries down, get all the same information. And if you notice, when we do that, the first thing that happens is that we gray out all the controls, and then they get re-enabled when all the information has been provided by the camera. So potentially you could have unplugged one camera and plugged in another, and then you could reconnect, you know. In the upper right here, we see the currently connected AIRS product. In this case, it's a Nyx 1280 by 1020 60 Hertz level 2 camera. A level 2 camera provides gain and offset correction, dead pixel replacement, and outputs 16-bit full-scale, corrected data. It's expected that that data is going to be consumed by a third-party frame grabber over camera link. If we look at the menus, there's a setup menu and an information menu. And now we're going to connect to a level 4 camera. We see we get an extra menu. And in that extra menu are the tools associated with the functions that we normally associate with that third-party frame grabber. The display of video, the control of palettes, adjusting the range compression and the other various image adjustments, point and shoot marking of dead pixels, snapshot capture, and sequence capture. There's 2 ways to open those screens. And so you can open from the menu. Now you can see a video screen with the image of a chair with some thermally interesting things on top of it. Or if we close that again, you can press this little video icon and it opens the same screen. All of these tools that we talked about are also available with icons in the toolbar on the left of the video screen. So we can open a palette. We can open the image adjustment tool. You can open the dead pixel marking screen. And then we can open some dialogues that help us do sequence capture, snapshot capture. So for now, I'm going to close those. And we're going to concentrate on the level 2 functionality that we might have. So you can either crop the image, or you can scale it to fit. In this case, I'm going to scale it to fit so that we have enough room for our Nyx Connect main screen. And now we're going to review the functionality of the main screen, basically. So the main screen provides all of the level 2 functionality. So it allows us to perform non-uniformity correction, which means we're going to calculate gains and offsets and do by doing 2-point corrections. It allows us to an offset adjustment, otherwise known as a 1-point correction, 1-point nuke. And it provides nuke table storage. So that once we've calculated a nuke table, we can save it or recall it. So let's talk about those in detail. So if we were doing let's just go an overview first. So we've done we've talked about non-uniformity correction. Then let's talk about dead pixel replacement a little bit. So dead pixel replacement is just what it sounds. All infrared sensors have dead pixels that need to be replaced. We have a number of algorithms that we use to detect and mark those dead pixels. That's in the dead pixel group. We also have the ability to store dead pixel maps and to mark dead pixels individually from this screen. In order to mark, well, we'll talk about that later in detail. And then we have a panel that allows access to the camera's FPA timing. These functions are normally configured. The one that's configured frequently by an end user is the integration time. You basically make the integration time longer, you capture more light. If you make the integration time shorter, you capture less light. If it's a high dynamic range scene, you would typically make the integration time shorter. If it's a low dynamic range scene, you would typically make the integration time longer. Whenever you change the integration time, you have to do a 2-point nuke for that integration time and tuck it away in one of these 4 available user nuke tables. The other timing parameters, like the number of clocks in a frame, the number of clocks in a line, the line sync delay, pixels per line, lines per frame, etc., are set typically in the factory, and they can be set by the user, but it's not something you should do lightly. You have to do a little bit of work in order to calculate the right values to be entered into this pane. They're exposed in this interface because we want our customers to be able to configure their cameras to meet their own needs, but they're not really what you would consider user level adjustments. They're there so that a knowledgeable customer can customize their camera. Same thing with timing and output control. This is a little more straightforward. You can turn the video on, you can disable the FPA output, you can enable or disable gain and offset correction. It's not something you would do every day if you're just using the camera, you don't do these things, but they're available in the timing and output control panel. And then finally, the FPA control panel basically shows the FPA's operating frequency and allows you to control the FPA's power. Lock control panel is used to configure a phase lock loop that generates the clock that is used by the focal plane array. This is also something that you wouldn't change without serious consideration. All of these timing parameters, including the clock control, all relate to one another, and you typically can't change one without changing the other. So again, this is not something that you would do it every day. This is something that you have to do a little planning for, and you would do if you, for example, wanted to change the frame rate of the camera, or you wanted to window down the camera. And finally, the FPA channels pane shows how many channels the FPA is outputting to the electronics in the Nucleus camera. And this is definitely something that you wouldn't change lightly. For the most part, I mean, you can change it and it'll send the command to the camera and it'll change, but the image will, I mean, it's not something you would do without changing the clock frequencies that you're running and some of these other timing parameters. So basically, the two rightmost columns here are things that can be done pretty safely, and the columns on the left are there so that customers that have the need to customize their camera have everything they need to do that, but it's not something that's done on a casual basis. So that's kind of a general overview of what's in this pane, and everything in this user interface is available for level 2, and then the image and the other screens that we already brought up are available at level 4. And it's important to understand that the camera decides whether the Nyx Connect application will run at level 2 or level 4. The Nyx Connect application interrogates the camera and asks it whether it should operate at level 2 or level 4. So you don't get a different version of Nyx Connect if you want to run at level 4. You get a differently configured camera to run at level 4. Okay, so let's see. So let's do a couple of things. Let's explain a little bit more detail of how non-uniformity correction works. So normally you would use a black body and set the black body to a low temperature, for example, 20 degrees C, and you would press acquire low temperature data, and it would capture 120 frames and average them, and save that, tuck that data away to be used during a subsequent 2-point nuke. Then you would change the black body's temperature to 40 degrees C, for example, acquire the high temperature data the same way, and we would go through the same process and save that data away to be used in a 2-point nuke. And then finally you press 2-point nuke, it does the calculations, and once you've done that, you can save the nuke table. I'll save the one that we have already done. I didn't actually do those things because I don't have a black body here. And on a camera with this resolution, it takes about 15 seconds to save that nuke table. And you can recall the nuke table. It takes a couple of seconds to do that. And so we just saved this nuke table to one of the 4 nuke tables that we support for the user. They're just numbered 1, 2, 3, 4. Yeah, and there's also a factory nuke table. So if we click on that, now that's the nuke table that the camera left the factory with. And so if you're making some changes and you get tangled up and you can't quite figure out which modification you have made that had the adverse effect that you're trying to get rid of, you can always go back to the camera's factory settings by selecting the factory nuke table. One of the things that's important to understand is that when you save a nuke table, it also saves all the camera's settings, including the FPA control word. So restoring the factory nuke table basically gets you a fresh start, and you're returning to settings that were the settings that were established in the factory before it left AIRS. You notice when we pick the factory nuke table that the Save Nuke Table button is grayed out. That's because we need the factory nuke table to be persistent so that it's always available to be used as a starting point. Okay, so that's pretty much it for, let's go back to table 2. Now, one thing that's probably interesting is that when we select table 2 gets automatically read. And you see that the factory table was a little grainier in this image. And that's because before we started this demo, I actually did a 1-point nuke in level 2. All infrared cameras drift and offset, and a 1-point nuke compensates for that. So let's go back to table 2, and let's do a 1-point nuke. So you put a thermally flat surface in front of the camera and press 1-point nuke. It takes a few seconds because it averages a number of frames, and then it should clean up the image, and it was already pretty clean, so that's the image we get. And it's also possible, if we're operating in level 4, to do that just by pressing this little icon. So let's demonstrate that. Put the surface in there. Also, I should mention that if you hover over any of these icons, a little tooltip pops up to show you what they do. So this one says 1-point nuke. And we basically just did the same operation using this icon. And the reason for that, it'll be obvious a little later, is that once the camera is really configured, you don't really need to use the main screen, and so you can minimize it, and then there's more room on your display for the other screens that you want to use. So let's talk about dead pixel replacement. The top button, Build Dead Pixel Map, replaces all of the pixels that have gains that are larger than 1.5 or smaller than 0.5. And it does a pretty good job of identifying the pixels that are, really misbehaving. It doesn't mark pixels that are a little bit nonlinear or blinking or those kinds of things. So then the second button says kill noisy pixels, and that button runs an algorithm that samples a number of frames and looks for pixels that are changing over time. The assumption here for all of this is that there's there's a uniform surface in front of the camera. And so when you click kill noisy pixels, it'll identify the pixels that are scintillated or flashing, and it basically looks over time and tries to find pixels that are misbehaving. Refined dead pixel map tries to find more dead pixels by looking at pixels that at say a middle temperature between the temperature that was acquired for the low temperature of the 2-point nuke and the high temperature of the 2-point nuke, at say a mid temperature, are brighter or darker than the median pixel value for the scene by a few hundred counts. And that tends to identify pixels that are misbehaving in a manner that makes them stand out just a little bit from the background. They're not unresponsive, but they're not responding correctly. Typically, it's the pixels that are behaving non-linearly. So that's what refined dead pixels does. And so typically when you're you've selected an integration time and you want to create a nuke table and a dead pixel map, you go through this sequence that we talked about in the non-uniformity correction. You go through this dead pixel replacement sequence in order. You build a dead pixel map, you kill the noisy pixels, you refine the dead pixel map, and then if you're satisfied with it, you save the dead pixel map. If there's a handful of stragglers, if you're working in level 2, you use the third-party frame grabber to identify the address of the pixel, the coordinates of the pixel, and you can mark them manually. Doing that is a relatively tedious thing to do, so you don't want to do that for many pixels. You want to find most of the pixels using these kind of global dead pixel marking algorithms. At level 4, there's a dedicated point and shoot dead pixel marking facility that we'll talk about in a little bit. Okay, so once you've built your dead pixel mark, you can save it. So let's save it. You can see it takes a few seconds. And once the dead pixel is marked, once the dead pixel map is saved, you can also recall it. And that's pretty much it for the things that you would do on an ongoing basis as you set up integration times in your camera. One thing I didn't mention though is that this auto recall button. So checkbox, excuse me, the auto recall checkbox. So if normally when you select a range, it automatically recalls the nuke table from that range. If you, let's do it again. If you uncheck this box, when you select the range, it doesn't do the recall. It just changes to the range. So the reason for that is that you might want to copy a range. So we just were using nuke table 2. If you want to copy nuke table 2 to range 1, you can just uncheck auto recall, select range 1, and then save that nuke table. And what we're accomplishing by doing that is making a copy of a table. So the auto recall checkboxes here so that you can disable auto recall in the case where you want to copy one table to another. Normally you would leave this checked so that when you pick a table, it automatically recalls. But if you, again, if you feel the need to copy an existing table, for example, if you wanted to start with the factory table and copy it to a table you're about to work on, let's do that just as an exercise. So I'm going to pick the factory table. It got automatically read in. We're going to uncheck auto recall. We're going to switch to table 4. And then we're going to save the table. And when this is done saving, we'll have a copy of the factory table in range 4. Let's recheck the auto recall button so that we won't forget to do it. And now it behaves normally. If we go back to range 2, we get our nice clean image. Okay, so let's talk a little bit about the menus we haven't visited yet. The info menu basically has an about box that shows you what version of Nyx Connect you're running, and a product info screen, which shows you that we're running a Nyx 1280 by 1020 60 hertz level 4 Nucleus camera, and shows the FPGA revision, software revision, serial number, cooler hours, and power cycles. All of this information came from the camera. Tools menu we've already talked about. In the setup menu, there's 2 things. Well, actually 3. There's the options menu. So auto disconnect, we've already talked about a little bit. If the camera fails to respond, we automatically disconnect. There are some instances when you maybe have a cable that isn't working right, or you have some communications issue and it's trying to get to the bottom of it, you might disable this feature, but typically it's left enabled. If you uncheck this box, the Nyx Connect will not automatically disconnect when there's a communications error. Show polling shows the 1 hertz polling that is normally going on between the Nyx Connect application and the Nucleus camera. This is going on all the time whenever Nyx Connect is running, but it's not something that you really want to see. So typically this is left unchecked. And then shared dead pixel map allows you, when it's checked, allows you to use a single dead pixel map for all ranges. So when you mark dead pixels, they're marked on every range. But we understand that some of our customers would prefer to have a dedicated dead pixel map for each of the ranges. So if you uncheck this, all the dead pixel, the dead pixel pane here for, the dead pixel storage pane disappears. And now when you save a nuke table, you will also save a dead pixel map. And the dead pixel maps, there's 1 dead pixel map for each of the ranges if you're operating this mode. My own opinion is that most customers should use a shared dead pixel map, because if the pixel is dead in one range, it's likely to be dead in every range. But in the interest of flexibility, we have provided this option to Nyx Connect. So final thing in the options dialog is a selection of the origin of the pixel coordinate space. So depending on which third-party frame grabber you use, the coordinate space might be 0 base or it might be 1 base. In other words, the top left pixel might be at coordinates 0, 0, or it might be at coordinates 1, 1. Nyx Connect level 4 uses 0 base coordinates, so the top left corner is at 0, 0. For example, the Imperx frame grabber uses 1 base coordinates. So if you are using level 2 Nyx Connect and an Imperx frame grabber, you would click this box, and now Nyx Connect is aware of the fact that we're using 1 based pixel coordinates. In fact, when I did that, let me see here, put these back to 0. If you notice in the dead pixel marking box, when I clicked 1 base pixel coordinates, these both changed to 1, because Nyx Connect knows that when you're working with 1 base coordinates, there are no pixels at 0, 0. When I changed back to 0 based, it didn't change because there is a pixel at 1, 1. So this is something you would typically configure once when you figure out whether you're going to use Nyx Connect level 4 or a third-party frame grabber, and you determine what coordinate space that frame grabber uses. So we're back at 0, 0. Camera communications. So the Nucleus that we're demonstrating has a USB 3 vision interface, so we've checked that. There's also a couple of virtual COM ports that could be used. There's a USB 3 vision virtual COM port. This is actually planned. We don't actually have one right now. But there's also a camera link virtual COM port. So if you're using Nyx Connect level 2 with a third-party frame grabber, you purchase a Nucleus camera with a camera link interface, you would typically click this button. And then finally, there's a depot port, which is only available if you had the camera open and a special cable plugged into a board inside the camera. So this is not typically used by anybody outside of the factory. The camera can support both a binary protocol and an ASCII protocol. The binary protocol is faster, but the ASCII protocol is more reliable. It has better error correction and checking. So we recommend that our customers use the ASCII protocol unless they have a very good reason to use the binary protocol. I won't do it, but you can switch back and forth between them just by clicking this, and the camera will accept whatever protocol happens to come down. It's actually always looking for both protocols. And if it sees a binary packet, it'll process it. If it sees an ASCII packet, it will process it. It's not modal. So that's the camera communications. And this is something typically you decide once, or if you bought a USB 3 vision version of the Nucleus camera, you would click USB 3 vision here, and then you'll probably never open this again. And the last thing here is a FPA configuration screen. So this camera has an SPF 207 FPA, and this is the screen that's used to configure the ROIC the SPF 207 heroic. And the definition of all of these settings is described in the SPF 207 IDCA, and it's kind of beyond the scope of this demo, but we basically have exposed every configuration parameter that's available in that ROIC, and they can be controlled from here. So if you press the FPA reset button, it'll actually send a reset signal to the FPA. It's not clear to me why that would be helpful, but it's something the ROIC supports, so we put it in the interface. You can read the FPA configuration from the ROIC, and it's nothing changed because we're running that ROIC this way right now. You can also, when you change this, you can load it into the ROIC. I'm not going to do it right now, but if you press this button, it'll load the configuration data that you've selected here and load it into the camera's ROIC. You can also, if you have, say you want to configure the camera in multiple ways. So one is with a full full width and height of the FPA, and another is windowed down, running at a different frequency. Okay, so we've gone through all of these menus. All of these menus are available in either level 2 or level 4. Excuse me, the setup and info levels are available in level 2. The tools menu is available only in level 4. Okay, so we know that our camera is configured correctly. It has good gain and offset tables. It has a good dead pixel map. So if we just want to operate the camera, we don't need the main screen. So let's minimize that. Now that we've done that, we can grow this to be the full resolution. And then we can start looking at the level 4 capabilities of the Nyx Connect application. So let me shrink this down a little bit. So right now we're in shrink to fit mode. If we change to crop mode, we get sliders that we can use to scroll. We show the image at full resolution. You can slide around the sliders to see different parts of the image. If you're in scale to fit mode, the entire image gets scaled down to fit the window that you're displaying it in. If you change the size of the window, the aspect ratio is maintained. You can't distort the image. So you put my hand in front of the camera so you can see that it's live. If you press this button, it pauses the image. So the image is now frozen. If you press this button again, now the image is live. And we already talked about the fact that you can do a 1-point nuke by pressing this icon. Before we talk about the other screens, we should mention that in the video screen, you can see the resolution of the camera's frame rate, the data rate of the data that's coming from the camera. In this case, it's 1.258 gigabits per second. And this final number you can see that's counting up is the frame count. It's there. I mean, the number of frames that have been processed isn't that useful, but it's useful to see that the camera is actually live, and this is a live frame versus if it was disconnected, this would stop counting. Okay, so let's talk about palettes a little bit. So we support 7 palettes. They're grayscale, sepia, iron, earth, air, fire, and rain. Rain is a very high contrast palette, so you can see a little bit of background noise, but you can also see a lot of contrast in the image. And all of these palettes are invertible. So let's go back to grayscale so it's obvious. You have white hot and black hot. Now, so in this case, the cold things look white, the warm things look black. And you notice when I change this, all of the palettes invert, right? So white hot and black hot applies to the color palettes as well as the grayscale palette. The image adjustment screen is used to control the range compression that we use to take the 16-bit raw data, or actually corrected data, gain and offset corrected, dead pixel replaced data from the camera and compress it down to 8 bits so that it can be displayed on your PC screen. Let's talk a little bit about what we're looking at here. The histogram on the bottom axis shows the 16-bit values that are coming from the camera. And on the vertical axis is a logarithmic representation of the number of pixels that have been counted to be at that level. So you can see that most of the dynamic range of the sensor isn't being used. We're using this fairly narrow dynamic range. This is a fairly narrow dynamic range scene. And it's important to understand that this is a logarithmic scale. So at this point, let's change the plateau to 10. I'll tell you about what that means in a second. So if we're at in this range, we're counting tens of pixels. In this range, we're counting hundreds of pixels. And in this range, we're counting thousands of pixels. So there's actually a lot more pixels in this little peak than there is in all of this big area of the history. Tens of thousands of values in a small graph. And so it's a little bit misleading. You know, it looks like most of the pixels are kind of here, but the reality is that most of the pixels are in this peak. So the dotted lines show the range that's calculated by Nyx Connect that identify the kind of the boundaries of the dynamic range of the scene. So let's change to linear, and let's talk about the top graph. So the top graph is the transfer function. And a transfer function is the thing that maps the 16-bit data to the 8-bit data. So along the bottom of that graph are the 16-bit levels coming from the camera. And on the vertical axis is the 8-bit data that's going to be displayed. That 8-bit data is either displayed as grayscale, which is pretty obvious when you look at this, or if we had picked a different palette, that 8-bit data becomes an index into the color palette. So you can see it basically maps camera intensity, camera levels, 16-bit levels, PC display values. So if we're in automatic mode, Nyx Connect determines what this transfer function should be automatically. And it does that at 60 Hertz. Let's go back to grayscale. And we have two automatic modes. One is linear and the other is histogram. So linear, self-explanatory. You see this is a straight line between the blue and the red dotted lines, and histogram is nonlinear. And what histogram does is it adjusts the slope of the transfer function so that you get higher gains where you have the most pixels. So if you don't have any pixels at a certain level, they don't count for anything and they don't apply to the histogram. If you have lots of pixels at a certain level, then we apply more gain to that level. And so if we look in linear, you can see a lot of the background gets washed out. The texture of the fabric on the chair gets lost. And that's because we've stolen display levels we've stolen display levels to be used in areas of the data that we don't really have any data for. And if you switch to histogram equalization, we're applying the display levels in areas that we know we have lots of data. And so you tend to get a higher contrast image and things don't get as washed out. And the reason we got this really subtle pattern in the fabric is because we have lots of pixels near those temperatures. And so that portion of the transfer function has a very steep part, in a very steep part of the curve, where if we were in linear, the whole curve has the same slope, and there's not enough gain to be able to show that very subtle pattern in the fabric. So we've already talked about the difference between linear range compression and histogram equalization. Histogram equalization will bring a bunch of detail out in the image, but sometimes it can also amplify noise and make the image look less natural. So we actually take the extra step of mixing the linear range compression with the histogram range compression, and we provide a slider that allows the user to adjust the level. The transfer function gets less linear, it gets more linear as I move this slider. So if you move it all the way to the right, you're really just doing linear. That's 100% linear. If you move it all the way to the left, you're doing 100% histogram equalization. And you notice that when we went 100% linear, there is no background noise. So when you went 100% histogram equalization, you see a little bit of scintillation in the background. That's because this transfer function is really, really steep right here. And we're applying really high gains to this image. So we get a lot of detail out of it, but we sacrifice the noise suppression that you get from linear. And it's a little bit different on every scene. So we provide this slider that you can use to kind of find the sweet spot where you don't have the scintillation and the image looks pretty natural. So you get the benefits of histogram equalization without the deficiencies of histogram equalization. The other thing, I'll put it all the way back to full histogram equalization. The other thing that you get is something called plateau histogram equalization. And that means that we don't count every pixel. Above a certain plateau, we just ignore that those pixels exist. And so the higher you make that number, the fewer pixels we ignore. So if I make this number, say, 10,000, we don't ignore anything. And now you see that the image got really noisy, Doesn't look natural. And this slope is practically vertical. So we don't like that. And you can mitigate that somewhat by changing the linearity. If you lower the plateau, excuse me, to say 1,000. Now we don't count any pixels at any 16-bit level that's coming from the camera that has more than 1,000 counts. You lower it further. Our default value is 350. That's a pretty good compromise for most scenes. So we got, even though we have full histogram equalization on, we got rid of most of the noise. The image looks more natural, and we can lower it further. And notice that when I do that, this boundary between the gray area, which are the pixels we're ignoring, and the white area, which are the pixels we're counting, moves. So let's move it down to 200. And for this scene, that might be a little better. We still can show the pattern in the fabric, and the scene, the image is a lot less noisy. So for this particular scene, that might be better. You put it all the way down to 1. You can't do 0. Then it's not much different than linear histogram equalization. You see this, there's a little bit of a dip here, but for the most part, it's linear. So the only thing that we're not applying to the transfer function are pixel levels that aren't counted at all. Like, we don't have any pixels at that level. So that's why there's this little inflection point here. But other than that, it's a linear transfer function. So from one extreme to the other, 10,000 gives you that. 1 gives you that. And we typically run around 350, which is usually a pretty nice compromise. And then we adjust the linearity to be about, 40%, something like that. And we find for many scenes, not every scene, that's a pretty good starting point for histogram equalization. Let's now talk a little bit more about linear. So you can run linear in automatic mode, where the dotted lines show you the part of the histogram that's being considered, or you can run it in manual. And when you do that, you can actually adjust the linear transfer function manually. You can either do that by adjusting the gain, where it makes the lines, moves the lines out or in. Notice in the top transfer function that these gray bands show up at the top of the bottom. And those gray bands show you the display values that aren't actually being used. You can see that the image is all washed out. We're only using kind of middle gray values, and those middle gray values correspond to the white band in the transfer function graph. And you'll notice that white band is where the automatic calculation of the limits of the transfer function intersect with the manual transfer function. So as I move this, you can see that that intersection point changes, and you can pretty much see that the image is changing to, if you move the level indicator, so if you move the gain indicator, the red and blue manual adjustments move in and out, but they stay around the same center. If you move the level, it moves both values at the either to the right or to the left. So if you move to the right, the image gets darker. You can see that by the band moving towards the dark part of the palette. And if you move to the right, the image gets brighter. You can see that by the white band moving to the top. If I move it all the way right, the white band went right off the screen. And now we basically have a washed out, white image. If I move it all the way to the left, then we have a dark image. We don't see anything unless there's some part of the transfer function in the area between the dotted lines. Okay, so you can make this manual adjustment by adjusting the gain and level sliders. If you want to kind of get back where you started, you can press the auto again, and it snaps those lines back to where they were. And when you go back to manual, you can also take this line on the graph and drag it where you want it to be. So if you're only interested in seeing, like, this part of this lunchbox, then you can make that adjustment yourself. You can either drag the red line or the blue line independently. So I typically just drag the lines around and let the sliders do what they do, but there are a lot of people used infrared for a long time that really want to see these level and gain sliders, so we provided them for them. So that's manual adjustments. You can also do manual adjustments in histogram. It's a little bit different. It's mostly useful for limiting the range that you want to apply the histogram in. It's not as useful as in linear, but it's still possible. You can see all the when you do manual adjustment in histogram mode, it basically ignores all values that are above the red or below the blue line and calculates the histogram only within that area. So you get still a nonlinear transfer function, but it's constrained to this area that you've marked by doing manual adjustment. Not that useful, but we put it in for completeness. So we've talked about image adjustment. Let's talk a little bit about dead pixel marking. So again, if you hover over this, you see the icon is called pixel marking. We just opened up our dead pixel marking dialog. At the same time, you see this little box here. So if you click on this image, I click here in this dark area, you can see this area goes dark. If I click on this area here, you can see that there's this transition between light pixels and dark pixels. You can either click on a space in the image, or you can drag it around the image. So pixels can be displayed as hidden, which means that we have done our best to cover them up. Dead pixels can be displayed as white. And now you can see the dead pixels that are here. So if I drag this over here, you can see that there's 5 dead pixels here. They can be displayed as black, or they can be shown at their original value. So you can see there's this white dead pixel in the middle, and around it are 4 dead pixels that are, this white dead pixel is actually stealing current from these other 4 pixels. So that's why this one is really bright and these are really dark. Well, they all get marked. If we marked, let's put this back. If we marked these, so you can mark a dead pixel just by clicking on it in a dead pixel marking dialog. Let's unmark them all. Show them as black so you can see that none of them are marked. If we mark this one, now it turns black because we are showing dead pixels as black. If we hide, you can still these pixels are still dark. So now if we mark those pixels, say that those are also dead, now now basically all those 5 pixel clusters are covered up. And if we again show them as white or black, you can see which ones are marked. You can show the original ones and see that really there were 5 dead pixels here, not just 1. Now, if you look at the screen, it kind of looks like there's 1 bright pixel, but there's really 1 bright pixels and 4 dark pixels. So they all had to get hidden. Let's put this back to hide. That's pretty much it. You basically, let's put these in white again so you can see them. You drag this box around to pixels that look like they need to be marked, and you mark them by clicking on them, or you unmark them by clicking on them. And every time you mark a new dead pixel, the dead pixel count goes up. You unmark it because that's not dead. And if you click on a box, right click on a box, it shows the coordinates of that pixel and the 16-bit level of that pixel that's coming from the sensor. If you click on a pixel that's marked dead and it's being displayed as white, it'll show 65,535. That's the maximum value that can be represented in 16 bits. If they're shown as black and you click on that, it'll show it as 0. That's the minimum value that can be represented in 16 bits. And if you click to show, you can actually see what that pixel value actually was. So a good pixel is in the 38,500, 38,300 range. So it's not much of a difference, but it's enough of a difference so that if you're in a low dynamic range scene and the gains are cranked up, you can actually see that subtle difference in the pixel. So it needs to be marked as dead. Let's go back to white. And if we go up in the corner here, we can see that there's a fair number of dead pixels up there. Down here, you can see a fair number of dead pixels. This array is actually a very good array. It doesn't have very many clusters. I don't see any clusters. But some of these are different shapes. If we can find one that's a little bit different. Oh, here's a little cluster. There's a little cluster of pixels, show it white or black. Hide it, disappears pretty well. Show it, you can see that all of these pixels were misbehaved. Let's hide it again. So the pixel replacement algorithm replaces dead pixels with weighted averages of neighboring pixels. And we have a fairly sophisticated algorithm that searches for the replacement pixels, and it uses a lot of heuristics to decide which pixels to use as the replacement pixels. And you can see from this demonstration that even when things are magnified the way they are in this image, that dead pixels are hidden here we're showing them, here we're hiding them. They're hidden very well. Okay, I think that's dead pixel replacement. Now let's talk about snapshot and sequence capture. Let's do. So by default, sequences are so you can choose by clicking on this where you would like to store your sequences. By default, they're stored in your picture folder in a subfolder called Nyx Connect, and you can decide what the name of this folder could be, but I think we recommend that you name it sequence, and so that you can discriminate it from snapshots. And but you can put it anywhere on the disk you want. This is just the default area. So you can basically navigate to it by using this dialog. And everybody that's watching this demo has done this on a variety of applications. So there's no reason to demonstrate it much further, but you basically navigate to the place where we want to store the sequences, and you click, let's pick sequence, and you click select folder, and then it gets saved here. Then once you've decided where you're going to save your sequences, you decide what you want to call the sequence, what you want to name the sequence. Let's call it test. And then you can also decide what you would like to call the individual files that are saved within the sequence. So the default name for the individual files is frame, but you can call them anything you want. So this is an SBF 207 connector, so we can maybe call it that. And then you choose how many frames you'd like to save, up to 120. For the sake of not using up too much space, I'm going to make it 30. And you can also choose how you want to save the image. So the default is TIFF. For sequences, we want to save, typically want to save 16-bit data that has come from the camera before it gets range compressed. So you can save the sequences in TIFF format, which is 16-bit data. You can also save them in ping format, which is an 8-bit RGB format that uses lossless compression. Or you can save them in JPEG format, which is a lossy compression algorithm that stores 8-bit RGB data. So let's save this in ping and TIFF format. And let's, for the fun, just change the palette. And let's start a sequence capture. So one thing to understand is that sequences get, oh, I did 120. So sequences get captured at frame rates, and then they get saved to the disk as fast as we can. So we save both TIFF and ping images. So it took a little while to save them, but they got captured in 2 seconds because we're running at 60 Hertz. So there are no skip frames. So now if we go look in this place on the disk, let's test. There's our test sequence. And you can see that we saved ping images and TIFF images, and there's 120 of them. And the ping images are color, and the TIFF images look washed out, and they're in grayscale because this is the 16-bit raw data that came from the array. If we display that in a TIFF viewer, you can see that it's not range compressed. But if we look at the image that was saved in the ping format, it is range compressed. You can see the chair, and you see a lot more detail. So typically, if you want a picture of the scene that's consumable by people, you save a ping image. And if you want an image that's consumable by, say, a MATLAB or something like that, then you save a TIFF image. Now, if we save another sequence, let me change it to fewer images. Let me change the palette again. Something different. Let me also change to a little less linear. And just save another sequence. So we didn't change any names. Now what we'll see is that this sequence got saved in test 2. Now you can see that we've got blue ping images instead of gray images, and the TIFF images look pretty much the same. So the sequence numbers get incremented automatically by the program. And the last thing I wanted to show you is that if you don't put any name at all in, and if we look in test 2, you can see that the file name is SBF 207 and they get sequenced. If you don't put any file name in at all and save a sequence, now we have test 3. You can see that the numbers, that the images are just saved, are called 1, 2, 3, 4, 5, 6. And so you don't actually need a base name if you don't want to, if you want them to just be numbered. Okay, so that's sequences. And typically sequences are just TIFF. Let's do just TIFF. Let's put this back to frame. And TIFFs store a lot faster. We can actually store TIFFs at frame rates. Here's TIFF 5, test 5, and those are just TIFF images. It's not typical that you save PNG or JPEG, but you can. And let's see, let's go back to grayscale. So now we'd like to demonstrate snapshot capture. We open it here. Or remembered. So when you open this dialog, if you haven't used it before, the default folder will be displayed, and it's usually in the pictures folder in a subfolder called Nyx Connect, and a subfolder below that called snapshots. So let's shots. Pictures, Nyx Connect, snapshots. And if we want, we could create a new folder called, for example, demo. And a file name called, let's call it test. Now, if we take a snapshot and we can see that we have a file called test1.ping. If we take another snapshot, now we have a file called test2.ping. If we click the TIFF button and the JPEG button, let's change the palette so you can tell something happened. Take another snapshot. We should get 3 files. So test3.jpg, test3.ping, and test3.tiff. Same rules apply. These are 8 bits. These are 16 bits. These are color. This is grayscale. These are consumed by people. This is consumed by programs. JPEG uses lossy compression, but it has higher compression ratios. The PNG uses lossless compression, but has lower compression ratios. The final thing we wanted to show you about this is that once you've set up this dialog, you actually don't need it anymore. You can take snapshots by pressing the little camera icon. And you can see let me change the palette so it's obvious. Captured 3 new files by pressing this icon. Let me change it back to just pings and pick a different palette. Let's do Earth. Let's do sepia because it's obvious. How about rainbow? Now if you press this, the other thing to mention is that you can press this as fast as you want. It'll take a whole bunch of those pictures, and it might take a while for them to actually get written to the disk, but they get captured as fast as you click. You open up one of those, you can see that there's this very high contrast image that we saved in Rainbow Palette. In closing, it's important to remember that there are hundreds of applications for high performance infrared systems, and most of the emerging applications like hypersonic, hyperspectral imaging, or extreme remote sensing require unique settings at the system level. Our clients typically tweak their camera systems to extract the data that they need. Nyx Connect will let you make those changes quickly and safely, allowing you to see the results immediately. Nyx Connect is digitally signed by heirs, and there are no automated updates or subscriptions. If you would like to experiment with the software in a camera system, we can send you a kit under a borrowed property agreement. If you have more questions or want to talk with our engineers, just send along a note from our website.